In this section, our goal is to be able to solve a system of linear equations in two variables algebraically using the substitution method. Examples. Find the solution to the system of equations. Remember last time we talked about how to find a solution to the system, and we did it by graphing. Let's review that briefly. So we took this equation, y equals 3x minus 1, noticing that it was y equals mx plus b. We found the y-intercept, negative 1, and we started on the y-axis at negative 1. Then we used the slope of positive 3 over 1. So from this point, we moved 1, 2, 3 over 1. And we continued to do that to have as many points on the line as possible, even moving backwards. Getting our straight edge, we connected the points to make a nice straight line. This other equation is in standard form. Using our cover-up method, I see x equals 3, nothing to solve for with x already by itself, and y equals 3. So the x-intercept is 1, 2, 3, and the y-intercept 1, 2, 3. And then we got our straight edge, and we connected the points. And we looked for the intersection. Where do the two lines meet each other? There's the intersection point at 1, 2. 1, 2. Well, today we're going to talk about another way to solve a system. Instead of having to graph it, we're going to use the substitution method. The substitution method is the way to solve the system algebraically. And remember that the solution will always be an ordered pair that contains an x and a y, and that it's the same x and y for both equations. Let's write down this system again. The first equation, y equals 3x minus 1, and the second equation, x plus y equals 3. Now remember, we said this solution is the same x and y for both equations. It satisfies both equations, which means whatever we get for the y in one equation has to be the same y for the other equation. So notice what y equals, all of this expression will be what y equals in this other equation. So this y, since it has to be the same as this y, if it equals this expression can be substituted into this equation where the y is instead. So what does that look like? Well, here's what we're going to need to do. Let's make some space for substituting this large expression in for the y. I'm going to move this x over, take out this y, and put the expression that y equals in the spot where y was. I'm going to have to move this over a little bit more. There it is. And now we've substituted what y equals into that second equation. Now we have an equation all in the same variable, all in x. Let's rewrite that equation. X plus 3x minus 1 equals 3. I don't have anything here to distribute, so I can take the parentheses away. Then I can combine like terms. X plus 3x is 4x. And then I can add 1 on both sides. So 4x equals 4. And dividing by 4, x equals 1. So I know that 1 is the x coordinate. Now I need to know what the y coordinate is. I will do one more substitution. Take this x coordinate and plug it into either of these equations to get the y coordinate. Well, this first equation is a lot simpler to use because the y is already by itself. So let's rewrite y equals 3x minus 1 and substitute what x equals in for the x of the other equation. So y equals 3. Instead of x, I'm going to substitute 1. So y equals 3 times 1 is 3, and 3 minus 1 is 2. So the y coordinate is 2. Notice we got the same solution that we did by graphing, but we didn't have to graph it. This is called solving algebraically, using the method of substitution. There's another way to check your answer with the calculator. Using the calculator, we're going to store each of these values in for x and y. So the 1, we'll type 1, will store into the x variable. Press enter. The 2 will get stored into the y variable. Now notice there's no separate button for y that's easy to press. We've got to press the alpha button to get to the y. Enter. Now we can type in this expression here and see if it'll equal this side. Well, we already know the y is 2. What does 3x minus 1 equal? It also equals 2. So that equation was satisfied. How about x plus y? So we can type x plus y and we get 3. And it's supposed to equal 3. So I see that this solution is correct. Number 2, let's solve this linear system by substitution as well. Here are the substitution method steps. First, we have to isolate one variable in one equation. Isolate means to get by itself or alone. Notice that unlike in the previous example where the y was already alone by itself, in number 2, none of the variables are already alone or isolated. So we're going to have to do that work. Now, which one is mostly alone? That's right. This x is mostly alone. So let's take this first equation, x minus 3y equals negative 4, and get this x completely alone. Notice that the other variables have a number in front, which would make it harder to isolate them. So to get this x to not have minus 3y, let's add 3y on both sides of the equal sign. So that x equals 3y minus 4. Now we're supposed to, second step, plug this expression into the other equation. So in this other equation, 2x plus 3y equals 19, where we see x, we're supposed to plug in what x equals in here. Remember that the solution is an ordered pair that is the same value for both equations. So whatever x is in one equation, it has to be the same in the other equation. So remember how we do that. We have to make room for where this x is. So let's move over what's in front. We'll move over the 2, maybe even move over what's after, and we'll take out that x. In its place, we'll put in what x equals. This expression, 3y minus 4. So instead of x, we have what x equals, 3y minus 4. Let's rewrite this equation. 2 times the quantity, 3y minus 4, plus 3y equals 19. Notice we have an equation that has only y in it now. And then we distribute. 2 times 3y is 6y. 2 times negative 4 is negative 8. Plus 3y equals 19. Combine like terms. 6y plus 3y is 9y. Add 8 to both sides. 9y equals 27. Divide by 9. Y equals 3. So the y coordinate is what we got first this time. Now we need to find the x. So we solved that one variable equation, and now we will use this value to solve for the other variable. So we're going to take what y equals, and we'll plug it into the other equation, into either equation. But the one we started with was the simpler equation. So let's take that first equation, x minus 3y equals negative 4, and plug in the y where the y is. X minus 3 times 3 equals negative 4. X minus 9 equals negative 4. Add 9, and x equals 5. So x is 5, and our solution is 5, 3. Finally, we want to make sure we're correct, so our last step is to check our solution in both equations. Remember how I showed you the fast way on the calculator? That's how we could do it if we had a calculator. Otherwise, we could plug it in and number crunch by hand. Let's take a look at number 3. Notice that they both say y equals. So the first step of isolating one variable is complete. Y is already by itself. Now remember, the solution, which is an ordered pair, is the same values in both equations. So whatever y equals in one equation can get plugged into where the y is in the other equation. So instead of writing y here, we can write 5x plus 3, and then we can write the rest of this equation, equals 2x minus 9. Now we have an equation with just x in it. Let's solve this equation. I want to get my x's together first, so subtracting 2x from both sides, 5x minus 2x makes 3x plus 3 equals negative 9. Subtracting 3 from both sides. Let's continue. 3x equals negative 12. Dividing by 3, and x equals negative 4. So we have the x coordinate of negative 4. Now we know we need to plug this in. Now both of these equations look pretty easy to plug it into, so let's pick one of them. I'm going to pick the first. Y equals 5x plus 3 is what that equation says. I'll plug in what x equals into where x is. Y equals 5 times negative 4 plus 3. 5 times negative 4 is negative 20, and negative 20 plus 3 is negative 17. So negative 4, negative 17 is the solution to this linear system. Let's look at number 4. We have to isolate a variable in one of these equations. Notice the first equation has a lot of stuff in there, so the second equation, which has less stuff, no coefficient for this y, would be easier to isolate. So let's take that second equation and get the y by itself. How? Well, adding x to both sides would get rid of the x. So y equals x plus 3. Now we'll take that first equation, negative 3x plus 3y equals 4, and we'll substitute everything that y equals, see y equals this, in for the y in this other equation. So here instead of y, we're going to put x plus 3. We're going to put what the y equals. And now we'll write the other stuff that's around it. In front of the y was a 3, in front of that was a plus, and in front of that was a negative 3x. After it was an equals 4. And now we can solve this equation that only has x in it. So first, I need to distribute the positive 3. Negative 3x plus 3x plus 9 equals 4. Combine like terms, and I have no more x's, so 9 equals 4. But that's not a true statement. 9 does not equal 4. That's not true. So remember what that means when the variables go away and we end up with a statement that's not true? That means we have no solution. Nothing we plug in for x and y will ever make these equations true. Nothing will satisfy them. And remember, when we have no solution, that's because the lines are parallel. If we were to graph this, we would see the slopes would be the same and we have parallel lines. How about number 5? Well, after looking at the x and y that have numbers in front, and in the second equation, the x and y, the x that has numbers in front but the y that doesn't, it looks like it's easier to isolate the y in this equation. So 2x plus y equals 6. I'm going to subtract 2x from both sides so that y is by itself, negative 2x plus 6. Let's take the other equation to plug it into. Negative 4x minus 2y equals negative 12. I see everything that the y equals, and I'm going to plug it in for the y in the other equation. So where the y is, I'm going to write everything that y equals, negative 2x plus 6, and put all the other numbers around it. In front of the y was a negative 2. In front of that was a negative 4x. And after the y was an equals negative 12. Now everything is in terms of x. Let's distribute. Negative 4x, negative 2 times negative 2x is positive 4x. Negative 2 times positive 6, negative 12, equals negative 12. Again, the like terms cancel out. I have no more x's, 0 x's. I have negative 12 equals negative 12. But this is a true statement. So if the variables all disappear and I end up with a true equation, that means everything that I plug in will work. So there are infinitely many solutions. Infinitely many solutions. Do you remember what that means graphically? We would be graphing the same line. See how it's going to give us similar answers like when we're graphing? Take a few minutes to write a short summary. Describe the method of solving a linear system by substitution. See you in class.